form. This is cool, right? Look at that. What's that little ring around there? Do you know? I don't think they know. I don't think they know exactly what makes these rings, but supernovas do this. But why it's a ring, right? Sometimes rings are not rings. Rings are just a sphere, right? If you have a spherical distribution of something and you look through it, sometimes it'll look like a ring because the edges, you know what I'm saying? The edges of it, you're looking through more material. Yeah, picture looking at a sphere. As you look through the edges, you're seeing it edge on, so it looks, right? Whereas here, you're only looking through 2 layers of it, right? But they don't think these things, they think these are actual rings. They're not just like apparent rings. Obviously, because this one is not seen face on, right? All of these types of rings would always be circular, but this one's not, right? And I asked the guy, I went to a lecture at OMSI, and I'm like, what's making those rings? And he goes, yeah, I don't know, right? Like, they don't know. Maybe they know now. That was like 5 years ago. They could know. You got another star birth where we have a star birth region, more star birth. This is like pictures. Look at all the crap. Look at all the crap that's not in, right? All the nebulous stuff, right? Okay, so life on the main sequence. You don't need to memorize it. This is called the proton-proton cycle, and when you do this little navigation thing, right? So do this, turn this in, I'll give you points for this, okay? When you go through here, they talk about the proton-proton cycle or the proton-proton chain. This is it, and it's not as simple. All you need to really take away from this is that it's not as simple as like 4 hydrogen atoms come together in an unlikely event, and 2 of them turn into neutrons, and then it becomes helium, right? Yeah? Right, because it's like 2 protons. No. It's like this whole thing that happens, right? And this is like one thing that can happen, and there's lots and lots of nuclear reactions that can happen in giant stars. So just think this is really difficult. Okay, there's lots of different reactions. Typically, though, this is the reaction that goes on, but giant stars have lots of different ones. Now, how do we know these high energetic nuclear reactions? How do we know what they are? Do we research them out of just the pureness of scientific thought, like, gee, let's invest billions and billions of taxpayers' dollars to investigate nuclear fusion and fission reactions for the pure basis of science, or were we just trying to make weapons? Were we making weapons? Yeah, we've got this down. We can simulate these reactions with supercomputers. Yeah. So who in the world wants unilateral, or who wants to have test bans worldwide? Which country is the most hip on banning all nuclear testing? We are, right? Why? We don't need to do it. We don't need to test nuclear weapons. We are so good at it. We've got the computers, we've invested the money, and right now, let's all stop. We don't need to do it, right? China, not so much. They still need to blow up weapons if they're going to develop weapons, right? I don't think they quite have the exact sophisticated stuff, right? Russia, not so much. They still, I think, need to blow something up to really test, you know. Okay, key concept. This is key concept. If you understand this concept, okay, you will be able to understand why stellar evolution happens. Okay? There are 2 things going on. There's an equilibrium, right? And there's 2 things, okay? Gravity happens for free. Gravity is always trying to crush a star, yes? Now, here's the crazy thing. The more you crush a star, the faster fusion happens, yes? Okay? So the more you crush a star, if you take the star, if you're like God or something like that, and you take the star and you start crushing it, right? As you crush it, nuclear fusion starts to pick up. Why? Well, because pressure increases the likelihood that fusion will occur because the molecules are getting closer together, right? And it gets hotter, which makes it more likely that fusion will occur, yes? Okay, if you actually compress something quickly, this is an adiabatic compression, it raises the temperature of something, right? And so as you crush it, the force you need to exert to crush it more increases. As you crush the star, the force you need to crush it farther increases. Well, gravity also gets stronger, but not at the same rate. Fusion eventually goes off the chart, right? And is gonna hold the star. So gravity is trying to crush the star. Fusion ramps up to the point where it becomes an equilibrium between fusion and gravity. Fusion trying to blow the star apart, gravity trying to crush the star. Now, if you had a star that's stable, and you're like God or something like that, and you crush the star just for fun. Here's what happens. The star crushes, because you're God and you can crush a star, right? You go like this on the star. And the star, the fusion's going to step up, and the star's going to re-expand. In fact, it might oscillate. It might expand beyond its equilibrium point, cool down, collapse, heat up, expand, cool down, collapse. It might go through several vibrations of that, right? And then it's the same thing. If you took the star and sort of like fluffed it up a little bit, like a feather pillow, right? It would cool down. Gravity would crush it. It would heat up, right? So it's a stable equilibrium. Now, some stars, by their very nature, are variable stars. They're doing a crazy thing where they heat up, cool down, right? Somebody had a hand up. Yeah.
I was just going to ask something about that. So that's when the stars that are really big, the big stars that are burning, are going through fusion at a really quick rate.
At a really quick rate.
That's why they die quickly.
Yeah, because here's the crazy thing, right? The more mass you put in there, the stronger gravity is, right? And then gravity crushes it even that much smaller, right? So super giant stars are going through fuel at an incredible rate to overcome that gravity.
So the more energy, the more mass you have,
Yeah.
the more energy is required to keep it from.
Right, and supergiant stars, if you look at this, where is it on the diagram, right? Is the mass of the star greater than twice the mass of the sun? Well, if it's less than twice the mass of the sun, it's doing proton-proton stuff. But greater than that, it's got other fusion processes it can do, because it's so dense at the center that it doesn't have to just do hydrogen. It's just doing everything it can, right? Everything's happening. It's more chaotic, right? So we're just sort of looking at a sun-like star here. So this is key concept one, right? And then this is crazy. They love to give you this stuff here. So this is a key concept, is that the burn rate, the luminosity of a star, is proportional to the mass raised to the 3 to 4, right? Somewhere between 3 and 4, right? It's about the cube of the mass. And so, if it's raised to the cube, it's going to burn out much faster than the amount of mass that it has, right? So if you double the mass, you're going to double the fuel, but you're going to burn it 8 times faster. Does that make sense? Yeah? Okay, so large stars are brief. They don't last long. Small stars are durable, right? There we go. Diminutive stars are durable, dim, and red. They're red. Right. So here is a main sequence, right? Remember that this is hot, or I'm sorry, yeah, this is hot, this is cold, yeah? Hot, cold, and then this is bright, this is dim, okay? And so here is our main sequence, and if you go here, the stars at the very end there last 100th of a billion years, right? They're just snapping and popping like firecrackers, right? These guys last about 0.1 billion years. They're about 1 billion years, 10 billion years. Our sun is like right here, about 15 billion years, right? And then 100 billion years. And somebody said, well, gee, if the universe is only 13.7 billion years, how do you know that it's going to last 100 billion years? Well, we can divide. We know how much stuff is there. We know the rate at which it's using it, and we can divide stuff by rate and get 100 billion years, right? Okay, 500 billion years, right? So as you go down here, they last longer and longer and are dimmer and dimmer. Kind of like, this class or something like that. I'm just kidding. All right.
The majority of stars, red dwarfs, are...
Oh, I don't know as far as population. Well, let's look. We're going to look at a HR diagram of a globular cluster. And I think they're just sort of, it's like a bell. There's not that many of those because they don't live long. Right, and I don't know that, I think these aren't all that common, but I could be wrong. Maybe it's hard to see these guys, and there's a lot of them. I don't know the answer is the truth here. Here's a chart, an HR diagram that apparently I scanned in a crooked way out of a book or something. But this is the size of them, right? There they go. They get super giant. And then I love this. Here's a type 0 star, 5. So apparently there's even bigger ones than this, right? Like an O. 0 would be like, here's some BO. So these guys are just super giant. You can't even draw a picture of them because yeah. So they just get giant, right? Here is Eta Carina, which is a star there's an upper limit to the size you can be. Eventually fusion is going to blow the star apart. Gravity or no gravity, it's just going to rip it apart. So this star, basically the brightness of this star looked like the stock market